Hello, friends. This is a video doing examples of magnetic field and force. So, example number one, if I have a proton going to the right in a field coming out of the board, we already know the field. So this came from right-hand rule number one somewhere else, and we can have a fun way working backwards of how do you get dots. We can think of fun examples of doing that, but that's irrelevant because it's given that this is a constant, relatively constant field. And let's say up here we have an electron also going to the right. Then if we do the right-hand rule, thumb to the right, fingers at your face. Take a moment. Thumb to the right, fingers at your face, you get a force downward. This is a -1, so we flip it and it goes upward. Positives will go one way, negatives will go the other way. A proton and electron enter a magnetic field, they split directions. They'll go in a circle because as this moves, the velocity changes direction. It goes down, and then our thumb is down and to the right at an angle. So look what I'm doing, right? Thumb is down to the right, and the field is still a dot. And I get that the force is now down and to the left, which is perpendicular. And it stays perpendicular the whole time, because remember, FB is perpendicular to V and B. Great. You can then set the formula for magnetic force equal to the centripetal force mathematical requirement. Because remember, if something moves something in a circle, it's got to be just right. And this is the just right, remembering that the charge of a proton is positive E, which is the same as an electron. Only for an electron, it's negative E. Great. Now, let's say that I have something like this. Let's say I have a wire, right? And I have a current going like this, and I have a proton going at some angle. And I just realized that this is not the example that I want, but I'm going to roll with it anyway. So what's going to happen is the current, I have my thumb to the right, right-hand rule number one, thumb to the right curling, I get dots up here, and I get X's down here. And they get weaker. Weaker, stronger. So that's really important, right? And the exact value is mu I over R. Great. Right-hand rule, thumb up and to the right, fingers out. I get a force that pulls this down. So it curves down. And as it curves down, it's getting a little weaker. So the force gets less, but here the force is down, and it does eventually come down. Here the force gets stronger. So here there's more, so it curves more. So here's the whole point. If FB is stronger, it curves more. Because FB is perpendicular to velocity, and this is for a free particle. Because if it's trapped in a wire, clearly if you have two wires, this isn't going to happen. But for a free particle like a proton or an electron, if FB is stronger, it curves more. If FB is weaker, it curves less. So you're going to have more curvature the closer to the wire. That makes sense, right? Great. Let's see, what's another good one here? Let's do one last one. Just a reminder that if I have a magnetic field pointing to the left, let's do a few examples here. Let's say I have a proton moving to the right. That's going to feel a force of 0 because it's not perpendicular. If I have an electron moving up at some speed v, thumb up, fingers to the left, I get a force out. So if it was a proton moving up, I would get a force out toward my face. The force would be out and it would curve toward me. But since this is a negative charge, I get a force into. So thumb up, fingers right, force away from me. So this is going to curve like into and around this. So it's going to curl around these magnetic field lines. If I have a magnetic field, and this one's going to curve this way, right? This one's going to curve that way. This one's going to curve this way. Still circles, but out of the page or into the page circles. If I have a magnetic field pointing left, and I have a velocity going like this. Here's the one I really wanted. That's what I was trying to do in the last one. Here, they're still perpendicular. This line is still perpendicular to a dot. So the magnetic field here is a dot. That's still perpendicular. Even though it's a diagonal, it's still perpendicular. Here, this one's not perpendicular. So how do we do it? Well, you either take the velocity that is perpendicular, or you take the magnetic field that's perpendicular. I'm going to take the velocity that's perpendicular. So this is still moving, but I'm taking the perpendicular velocity. V perpendicular determines FB. And in fact, if we were more exact, we would say this is V perpendicular cross B. And it's a cross product. To be a little less exact, we're just going to say V perpendicular times B. And this ends up being, what is it? V sine theta. In standardized tests, you memorize QVB sine theta. That's on your like equation list. Just like FD cosine theta for work, it's QVB sine theta for magnetic field. I'm not really going to get into that, but conceptually, there's some fun examples of this. This is one of them, that if you have a charged particle going at an angle, everybody do it. Thumb up, finger left. Same here. You get a dot and it'll curve outward, right? And let's say that these field lines are here as well, right? They're everywhere. Constant B. And it's going to therefore curl toward us, right? It's going to curl this way, but it's going to keep moving this way. This parallel, this is unaffected. Right? So V parallel is constant the entire time. Like it has momentum, it has inertia in that direction. So it's just going to keep going this way, but it's going to curl in a circle. So what's that going to be? It's going to be like a curly helix like this. So what does that mean? That the particle is trapped. Ooh. And if you look at video of ready? I'm doing it. This is going to be fun. If you look at video trapped radiation. Ooh, that's really cool. NASA's got a website about it. That's really kind of fun. You see how it's like circulars, right? So this is charged particles being trapped by the magnetic field of the Earth, which is really fun. But I wanted to show you, like, if you see pictures of the sun like this is in ultraviolet, which is why it's colored green. It doesn't actually look green. The sun is white. But you see these like solar coronal, those are magnetic field lines. That's a coronal mass ejection where the magnetic field lines stretch and snap like rubber bands. And see these how you can see them is that particles have been trapped around them that are at thousands of degrees, so they glow. So you can see the magnetic field lines because they are trapped and doing like helical shapes around them for this reason. That's it.